Okay, one of my favourite things today, use intelligent U-substitution to find non-simple integrals. So, by simple integrals what I mean is basically you can just go to a formula sheet and look them up and you're done. And although you do have formula sheets for some non-simple integrals, a lot of them you start to lose detail pretty quick if you don't know what you're doing with them. So, what's the basic gist of this? I'm going to get the integral of something. It turns out that you can fiddle around with this into this form. Now, maybe the more obvious way of thinking about it is that, oh great, I'm dividing by dx and timesing by dx, so I can cancel those out, and that's like the engineering way of thinking about it. It's not really rigorous mathematics. However, for Spec, that will actually suffice just fine. So I'll leave it to your university level mathematics professors to argue about exactly why that is so stupid. But for us, that will work perfectly fine. We're going to stay well within those bounds. Okay, so let's say we've had this function. Okay, great. Well, if I wanted to integrate that currently, I'd have to expand it out and then integrate, and I'm stuck with this really long polynomial, which sucks, but hey, it's not the worst thing in the world. Is there another way of thinking about this that maybe keeps things a bit neater for us? Alright, well, let's think about this function for a second. What's complicated about it? I've got a function inside a function. I've got essentially a chain rule sort of thing going on. Well, there's no integral chain rule per se, but we can think about it a couple different ways. Let's, for a start, this U substitution, let's replace all this complicated stuff with U, because if this was just x squared, we'd know what to do. So I'm just going to replace this with U, so I get U is 3x minus 4. Cool, okay, well, if I've got U, I'm going to need du dx, so derive that, I get 3, and in my original expression I'm going to have this dx floating around, so if I rearrange that, I can get dx equals du over 3. Again, we're just treating those as treating those as though they are fractions. There we go. Cool. So once all that's said and done, okay, we still just want to integrate this thing. So integral of this, well, we're now calling that bit u. So that's now u, which I should have written in purple. Where my text has gone? No, it doesn't matter. There we are. Okay, so I should have written that u in purple just to make it clear that that's the thing that I've replaced with this. There we go. That's looking a bit better. Cool. It's still squared because the original function was squared. Okay. This times by a third came from replacing the dx. Okay, so the dx is actually du on 3. So 1/3 times du. Okay, well, I can shuffle this because we know our integration, not laws, but it's linearity, so we can move that 1/3 out the front because it's just a constant. Great, okay. Integrating u squared with respect to u. Well, that's nice easy. That's 1/3 u cubed plus a constant. This whole thing's being multiplied by that third, so 1/3 multiplied gives me this. The u was actually this, so we plug that in. All of that's to the power of 3 plus some constant. Now, I've put a star there because that constant technically gets multiplied by this 1/3, but we don't know what the constant is in the first place. So I could write 1/3 c, but then that's still just a constant, so it's still just a c. I'm just putting a c star to indicate that this value and this value are necessarily different by a factor of 3, but we don't care what they are per se, they're just representing some unknown constant. So that's the basic gist of this. We pick whatever is the most complicated part typically, we replace it with u, we figure out du dx, and therefore figure out that dx equals some du over something typically, and then we try the integral from there. Okay, well, here we've got something far less straightforward. We can't even expand this to do it the old way now. We definitely need something more intelligent. Well, what's the most complicated thing here? I've got a square root over this function. That's the most complicated thing. If I just had the square root of x, that'd be fine because I can change that to x to the power of a half and then we're good to go. So I want to replace all this. So u is now going to be 4x squared minus 5. Same as before, derive it. Du dx is 8x. And then find dx, so just shuffle around, you end up with du over 8x. Great, I want to integrate this thing. Okay, so integral, this thing I haven't touched yet, so that's still 3x. Haven't changed the square root, that's still there. This thing is now u. Okay, multiplied by, whenever I do an integral, dx at the end, but I'm going to replace the dx with du 8x. Cool, so I've got this, brilliant. Alright, well, what does that allow me to do? Well, I've now got this 3x divided by this 8x. Well, the 3 divided by 8 can come out the front, because that's just a constant multiplying everything, a scalar. X divided by x, oh, that's handy, they drop off. Now back here, I didn't know how to integrate this because I've got x's and u's in the same line. I can't integrate when I've got two different variables in there until we do multivariable calculus, which we're not going to do. So I need a way of getting rid of either all the x's or all the u's, depending on what's on the end. I've got du on the end, so I want to get rid of all the x's. Unsurprisingly, conveniently, those x's have cancelled out. Great, so I end up at this point. Fantastic, well, we know how to integrate that. So this is now next line, the 3 on 8 just sits out the front. Integral of this gives me this. Don't forget your plus c. Simplifying all the fractions, we get to here, and then last bit, just sub in that u back again. Sometimes you'll be able to simplify this a little bit further again, but in this case, it's not going to get any prettier than that. So we're done. Again, I put the stars on the c's just to indicate that the c and those c's are different values. Cool. Well, let's do something a little bit weird. We'll do something with trig in it. Cool, I've got a product and, well, you can think of this as a 3 product, or you could think of it as a chain and product. Either way, you've got more complications in there than you know how to deal with typically with integration. So what we're going to do, replace with u whatever is the most complicated part. Sine squared is most complicated, so I'll replace I'll replace sine with u. Derive that, we get cos. Shuffle around, so we get dx is equal to du over cos. We want to integrate this whole thing. Great, well sine is now u, so this is the integral of u squared by still cos with du over cos in the end. Great, cos and cos cancel, that's what you want. You want to get rid of all your x's, so you've only got u's and du's left. Cool, so I've got this, well that's a nice easy integral, and then we just sub in u again. So it actually ends up quite nice. The really good thing about integrating is that to check it, it's usually pretty straightforward because you're just running differentiation, which hopefully you're very comfortable with at this point, given how much practice we've done. So it's easy to check them and check if you've stuffed up. So I'd invite you to derive these, make sure you get back to where you started. Next bit. Okay, so now we get something that's a little less obvious perhaps. Okay. We've got something divided by the square root of some ugly function. Well, clearly the bottom bit's the most complicated, so we'll replace that with u. Okay, I go du dx, figure out dx, great. Okay, I've got 3 over the square root of my complicated thing u, times by, and I've just moved the negative up the top just to neaten things a bit. So I've got negative du over 2x plus 4. And now if I look at this, I go, oh dear, hang on, I've got this extra x floating around. That's no good to me. If I had an x up here, then perhaps I'd be able to cancel or do something, but now I've got an x floating around. This is dead. I can't do anything with that because I've still got x's trapped with my u's and du's. So we have to be a bit more intelligent now. Well, this is still definitely the most complicated bit. Maybe we should just shuffle the terms around and see what else we can figure out. So I could change this into that and then say, well this 10 doesn't actually bother me that much. It's this part that bothers me. So I'm going to replace that and now I'm going to call it v, just because I already used u. You could just jump straight to this if you wanted, and then you'd be calling your u's v's. Your v's u's, that's fine. But since I already used it in an illustration, I'll change up to the next letter, which would be v. Cool, alright. As always, you derive that, equals 1, that's quite handy, so dx must be equal to dv. Cool, integrating 3 over the integral of u, well that's that, but remember this was v, so I've got 10 minus v squared. My dx became dv, so I've got dv. Now we look at this and hopefully in your head it harkens back to 7b stuff, the integrals of inverse trig functions, because we've got a constant over the root of squares in there. So that's our rule that we're applying in case you can't remember it off the top of your head. But basically it's just plug and chug. So we've got 3 on top because that's just multiplying everything. I could have pulled it out front. Root a, so a is going to be root 10 because we've got the squared on there, don't forget that. And our x in this case is v because we're just substituting letters around. Cool, so we get this guy and then just expand through and we're done. And replace the v back again. Cool. So sometimes it's not so obvious what to do. You can very commonly end up in this trap. At the start, a lot of the time you're just going to be plugging away at it, just throwing different variations of things. And despite how good you can get at these things, a lot of the time, sometimes the first thing that you guess will be a dead end, but usually depending on what spits out afterwards, that'll usually give you a clue as to what to do. Unfortunately, the best way to get good at this is experience, which I know isn't particularly helpful, but at the end of the day, the more of them you see, the better your intuition gets. And the more commonly when you see something go wrong, you know why it went wrong already. Cool. Next guy. So we've got a linear over a quadratic. Great. Well, the quadratic is the more complicated bit. Something else that you can do for this is split this up into partial fractions. And that would be just fine, so long as the top power is lower than the bottom power. You can potentially do that just fine, and then integrate each of those successively, and that's totally fine. However, if you've got this is 1 power less than this, and they're both, what do you call them? Polynomial, and this is 1 power less than that, then you can just run this all in one hit, at least potentially, without too many exceptions. So I'm going to make u the bottom thing, derive as before, shuffle around to get dx. Great. Top over complicated u. This is just the dx replacement. Great. If I take a look at these, oh brilliant, this is exactly 2 times that, so I can shuffle that out. If this wasn't exactly 2 times, then you're probably going to have a bit of a bad time because you're going to have an extra term floating around. That doesn't necessarily break it, it just usually means you have to split up your integral into more and more parts until it does finally work out. But this one's quite kind, unsurprisingly, by construction. And then we end up with a nice basic integral, which hopefully we know is just ln. And then we just substitute back through. Cool. The only extra complication that comes up, well, other than just being complication upon complications, the only other different kind of complication is when you're trying to do it with a definite integral. Keep in mind, this is saying, do this integral and then take x to be 2 minus x to be 1. So if we do our U-substitution, we get to this point, x is equaling 2, x is equaling 1 for all our integration. We go through the normal stuff. We end up with whatever it was, this guy. Okay, that's fine. So I want this integral, which has already been integrated, but I want it when x is 2 and x is 1. Well, that's no good because I've got u's in here now. So I need to go back, or do it at the start, as I've done, and rearrange this to figure out what x is in terms of u. So I go, okay, x is 2. Okay, well if x was 2, 2 minus 1, u must have been 1, so u becomes 1. If x was 1, then u must have been 0. So now I can replace those onto those, substitute in accordingly, and then just calculate through as normal. So the vast majority of this is just pick the most complicated thing, replace it with u, and then do exactly what we've been doing in red. And then just work your way back through. Make sure all the x's cancel themselves out nicely. The other part, the minor part to that is that you're going to have complications upon complications. Just power through and get your practice in, because it does just take a lot of practice to get good at this. The second actual proper part is when you've got definite integrals. Always, I highly recommend, as soon as you start with your integral, whatever this is, just write x equals, right? If it's dx, if it's dv or whatever, write v equals, so that when you get down to these parts, you'll recognise you'll have u, and then you'll have all of a sudden x, and you go, ooh, right, I've got to switch that out. Because it's very, very common to get pretty good at the integrating, and then stuff up here because you just go, oh, okay, u is 2, u is 1, because you've only written the 2 and the 1. Switch out, write whatever variable it's actually working in, or alternately, before you even write this 2 and 1, switch out into terms of u. So this is already 1 and 0 if you do it that way. Either way, just make sure whenever you've got a definite integral, if you're going to do a U-substitution, switch out those terminals. Cool. Email if you get stuck at all, which will almost certainly happen for some of them. Best of luck to you though. Cheerio.